We'll now look at a few more things that we can do with functions. We start with looking at the inverse function. In order to define the inverse function, we do need our function f to be a bijection. That means we need it to be both 1-to-1 and onto. The inverse function assigns to every element of b the unique element of a such that f of a is equal to b. And this is denoted by f with a little -1. And the idea here is that we're going backwards. Before, we would have an ordered pair like a comma b, and now with the inverse function we have b comma a. For example, if I have this function from z to z defined by f of x equal to x plus 7. F inverse means we need to undo this function. So instead of adding 7, we'll subtract. And this will be the inverse function. For example, if I stick in 0 to f, I would get an output of 7. And if I stick in 7 to f inverse, I would get an output of 0. We can also talk about the composition of two functions. Here, I would need a function that goes from a to b, and then another function that goes from b to c. Then we define this composition, f of g of x, to be f of g of x. The idea is you put a value into x, you get its output, take that output, and then stick it into f. For example, I have these functions 3x plus 2 and 2x plus 3. If I want to find g of f, this means g of f of x. We know that f of x is 3x plus 2, and then this would mean changing the x in my g to 3x plus 2. I would get 6x plus 4. And if I try to go the other way, f of g of x, well then I have f of g of x. I know that g is 2x plus 3, so now I need to change the x's in f to 2x plus 3. And this would give me 6x plus 9. So f of g and g of f are not the same thing. And we have three very important functions that have names. The first of which is called the floor function. The floor function is the largest integer that is less than or equal to x, and it's denoted like this. It kind of looks like square brackets, but it's missing the top part of it. For example, if I want to find the floor function of 2.4, I need the largest integer that is smaller than this, which would be 2. Similarly, 5.9, the largest integer that's smaller than this is 5. This one would just be 1. I actually need the largest integer less than or equal to, and 1 would be satisfy this equation. In addition, if I try to do -3.6, the largest integer that's less than this would be -4. In contrast, we also have the ceiling function. This is the smallest integer that is greater than or equal to x. When we dealt with the floor function, we went down to the next integer, and with the ceiling function, we're going to go up to the next integer. For example, the ceiling function of 2.4 would be 3, since that's the smallest number integer that is greater than 2.4. The ceiling function of 5.9 would be 6. The ceiling function of a whole number is still just that whole number. And the ceiling function of -3.6 would be -3. The last function we'll look at is called the factorial function, and this is denoted f of n is equal to n with an exclamation point, And what this means is we multiply n by n minus 1, by n minus 2, and we keep going all the way down till we get 2 times 1. Therefore, we just take the number n, multiply it by a number 1 less, 2 less, etc. until we get down to 1. For example, 3 factorial would be 3 times 2 times 1, which is 6. If we tried something bigger, 7 factorial would look like 7 times 6 times 5 times 4 times 3 times 2 times 1. If we tried to look at something like n plus 1 factorial over n factorial, n plus 1 factorial would mean n plus 1 times n all the way down to 2 times 1. N factorial means n times n minus 1 all the way down to 2 times 1. And we can see here that we have this n all the way down to 2 minus 1, or 2 times 1, on both the top and the bottom. Therefore, they're going to cancel, and this simplifies to n plus 1.